My name is Roger Fritz. I live in Paso Robles, California. Um, I want to thank everybody for coming in this morning. Morning some places obviously a lot further than waiting that, maybe mid-afternoon, midday. Technology today amazes me how much we can interconnect and share information and help everybody to become better in their field of work and efforts. I was fortunate enough. My father started back in 1953 installing wind chargers before there was even the power lines out in Nebraska, and he also moved on from there, built several companies, and you can see on my right-hand side, my dad started me very young. I was at the age of 10, rewinding electric motors with him. From then, went on to build companies, remanufacturing motors up to 5,000 horsepower, plus fans, steel, power, multiple things. I'm very grateful for his influence in my life. And it's carried on. I have a couple of sons having businesses in the Midwest, one in the Midwest, one on the East Coast, in the VFD control businesses, also 508 UL shops. And again, that's my grandson, so he's in fourth generation. Coming forward, I've spent a lot of time with the power companies over my career, 40 years now in the electric motor industry, working on pilot projects for VFDs applications, from everybody from National Grid, PG&E, Southern California Edison, Eversource, many companies for many years. And it came from my electric motor experience. I was very fortunate to have some very highly qualified. And from that, then over the years, I've built a group and a network of over 30,000 people inside LinkedIn that are worldwide in motors, pumps, high horsepower equipment up to 10,000 horsepower that I'm partnered with the group out of New Jersey. And also in England, I partner with a group that is involved in VFD technologies, everything from power generation applications to, the list goes on and on. So I want to start with, as I always like to start with, is that it's very important that we really are aware of what this, electric power is. You can't see it, so it's very important that you don't touch it unless you know what you're doing in opening panels, controls, especially in control technology, because a lot of it has lower pilot voltages and those things. I'll go on to the next slide here. This is my contact information, engineering at AC-DC-HOTLINE. My phone number if you need to touch base with me. Please also ask any questions as we go along. There's a chat section. You can write that at the end. I will review them and open it up for discussion towards the tail end, of the discussion. I'm very heavily involved also with a group called Nikola Tesla's Today's Solutions and Collaborations. It's a LinkedIn group. You can type it in, Nikola Tesla, and you'll see this, and you can request to join. There's approximately, I think about 2,500, maybe almost 3,000 people now involved in that. And from that group, they share concept ideas, information, postings, on from a lot of different projects, because I truly believe Nikola Tesla was definitely a hidden gem. I know Elon Musk is definitely connected to a lot of his previous designs, patents, multiple things. A brilliant man. I actually own a copy of the book, which I call Tesla's Bible. It was written in 1918 or something like that, but it has all about rotating machines, details, and equipment. And from that, it highly helps me to learn. And I always learn from others also, and that's all about the sharing and collaborations of information. So I do highly recommend you join this group. Some of you have probably been on before, but I always like to play this little video to start.
When you think of electricity, you think of Edison. But there is one electrical genius who is nearly forgotten. A man who dreamed of giving the world an unlimited supply of energy. His name was Nikola Tesla. This is the story of a modern Prometheus who changed the world with electricity. It was Nikola Tesla who captured the power of Niagara Falls with his alternating current system and made it possible to transmit electricity to all of America and the world. Suddenly knew he could recreate this rotating field by powering the coils of a motor in different steps or phases, like the pistons of an engine. The resulting forces of magnetic attraction and repulsion would literally twist the rotor in a circle, the electrical equivalent of the wheel. And all this was accomplished with alternating currents. It would soon turn the wheels of industry around the world. Tesla was ready to unveil his motor to the world.
The subject which I now have the pleasure of bringing to your notice is a novel motor which I am confident will let...
So the reason why I start there is because I think it's very important that we discuss the simplicity of what we're actually doing. And then a person finds it much easier to, define and figure out where, problems come from. One of our main discussion points today is submersible motors. And the reason for that is they do have a high failure rate if they're not controlled properly and actually understood properly. So I do want to go back to, but they all have a rotating field, on the outer part. And what they're basically discussing, this is how they're wound, so that this shows, a single phase with just basically one phase of, a 4-pole, rotating machine. A 3-phase will have all of these, it'll have 3 sets of these, so it'll have an extra set in between each of these. And then you have 3 phases of power, 3 sine waves going out, which give it more power and torque. The rotors can be of various types. A lot of them are induction motors. So the outer coil actually induces power into a field of a barred rotor motor, and it builds a magnetics on the rotor, and so they repel each other. And as these rotating fields move through, they make the motor turn, obviously. The initial ways of, most motors were basically off of, just contactors. This shows a regular magnetic starter contact. It shows it basically has the 3 set of contacts here that are connecting the 3 phases to the motor, and they just simply turned it on. The disadvantage to that was the motor actually would have anywhere minimum of 3 to 6 times the running current. So if the motor is rated at 100 amps, it could take as much as 600 amps to start it. Well, you would have to have a much heavier generator in order to get that done. So the power companies that came in and said, look, you can't start many motors across the line. So they, came up with various ways to do it. So some of the next ways were, like this is where the motor's windings were split up. This is a part winding start where 3 lines come in, and then after a timing comes in, then it would bring in the second phase. The issue about that is that different types of loads didn't like it as well. And so it wouldn't always start quite correctly. So on pumping applications. So then they came up with the Y delta starters, where they basically were taking, again, those windings that I was showing you earlier. They were doing configurations of connections to, look like I got an arrow on there making lines, but what happened what happens is that they put um, the voltage drop across the windings changed how fast the motor would come up to speed, and it would also would control the lower current. So they had where you had 3 contacts come in, connected it in a Y configuration, and then converted it over to the delta connection and was back across the line. A lot of those are out in older applications that still exist out there. Then came about is the soft starter, where the motor would be started, and these are Thyristors or SCRs. And basically, what happened is it came on, then it would slowly. This idea what they look like, but what it did is it would slowly bring the power on to the motor as it came up to speed. So as you're looking at the sine wave here, what it would do is as it came on, you could see it would just triggered on a short period of time as it would start. And then it gradually went more further and further. And then towards the end, when it gets up to speed, it's got it on, full power across the line. And then they shunt this SCR out. The advantage to this is, the one is you don't get heating inside the control box as much at all. And when they're running, so they can be, pretty much totally enclosed. The issue is you do have to, tune these, to the application. Very, very user-friendly technology. Then came about the VFD technology, which is what I started to get trained in the 1980s. I went to some very early on classes with Toshiba when they used to use hockey puck style looking transistors, not the block styles that are out today. And this design basically had a diode bridge front end, meaning that it would take the sine wave and it would convert it all to DC bus filter power. That's what this is a line reactor to reduce current surging. And then this is a capacitors that are inside. And all it was doing is basically building us a DC bus supply inside the drive control. Then with transistor outputs, and the original ones I started out with were GTRs, which were gated transistors. Then they went to isolated gates, which are now, but what we're doing is we're building what they call PWM, pulse width modulation, that feeds the motor. So again, this is the output of what it looks like, to the motor itself. So it's not sinusoidal voltage. It's actually PWM. The red is the resultant current waveform that feeds out to the motor. Some areas that I did want to bring up that are crucial when you're building these kind of application systems is to understand that the output waveform not being sinusoidal, as it shows down here on the right, it's this PWM, that we're basically doing the same thing that they do in radios and in frequency controllers and those things, is actually creating. So this is the voltage, the black here, and this is the actual current draw from these diodes triggering back and forth dependent on the load inside the drive circuit. So as we're feeding this capacitor to build this, it doesn't draw the power linearly. It's called nonlinear power. Well, what happens is when this pulses like this, we're creating 100 twice instead of just 60 cycle power out there. All of a sudden, we're seeing 120 hertz current forms. which then inherently go back and start affecting the actual voltage waveform. So from that voltage waveform, it's very important to understand that we've got to keep this below the threshold of what the winding is originally designed for. And one of the factors that comes up is that as you go longer lead lengths coming out of the output of the motor, anywhere from 100 feet and above, you will these voltage will attenuate. They will actually increase. So you'll see these spiking voltages here that are going above. That's what's causing some of the failures in submersible motor applications, because the voltage windings were designed maybe at 1200 volt wire, and sometimes we're seeing spikes of 1500 volts, 2000 volts the longer that you go, because you get that harmonic effect. So what we're doing with the VFD is we're actually regulating this PWM, which is then changing the the current to the motor. And so we can go anywhere, like this is a 10 hertz, but you can see the pulses are spread out, and then this goes up to 20 hertz. The pulses are a little bit closer, and then they're going further. And inside of a VFD, they also have what they call carrier frequency, meaning how fast are these pulses happening. Some of the earlier drives, or VFDs, same thing, were just 6 pulses, meaning they had six pulses trying to control that waveform. You heard that a lot in the motor. You'd hear a lot of audible noise. Then they went up to roughly 1200 hertz, 1500 hertz on the transistor firing. Again, you could hear the audible noise coming into the motor. Now they're as high as 15,000 to 20,000 pulses per waveform. So it becomes a lot quieter. You can get better regulation on the motor, some of those things. Let's see. So we had this is a little bit about the principles of the application of motor and speed. This is actually a main circuit drawing of original drive that again was, you may have a soft start resistor in here. Again, it's just to slow that capacitor down on how fast it comes up. It's all for surging. And then what I want to discuss today is design of various submersible motors that are out there. There are a lot of material types that you want to look into, which are also an indication of life and failure of a submersible motor. For desalination, you need to have the motor wound and designed different, but definitely these end caps, whether they're stainless steel, all of those effects of material life are key. It's not just one motor fits all. Come back to that. And also, the design and the quality of the copper wire, the bearings, the laminations. I'm involved a little bit with Sars, and they are very critical to the design of their motors and to the proper copper wire, bearing types, laminations and materials. Even the different types of windings that are available. They also build in heaters, vibration sensors, special paint. So back to the original VFDs. This is actually a circuit drawing that I had from the early 80s, before we had all the digital capability. And you can see that everything was done what they called analog. So these were small little potentiometers inside the VFDs that you tweaked with a tiny little screwdriver. And so as you set up the PWM and the setups, you had to adjust the voltage, you had to adjust the, the tuning frequencies, the upper limits, the lower limits were all done, in a analog format. The frequency and the carrier frequency, all that decel, XL were all adjusted by potentiometers. They didn't have all the, the higher end type of keypads that are on the drives today. And I think that the drives have become overcomplicated for a majority of applications. What we're doing is fairly simple circuit, but that's why it's important to understand that we're a basic product, and then understanding the actual keypads. Don't be afraid of them. You basically power the unit up. They have auto tuning capabilities. You can program them. You turn them on, you program them, and these basically just scroll through. And what we're dealing with is our hertz, our amperage, our voltage, our percentages. Just to, keep it simple. We're basically a frequency and a voltage control is what we're doing here. Forward, reverse buttons, and all of these buttons are controllable then by how you assign them, inside the drives. So again, take off your fear glasses and just say, we're a simple circuit. We just have a lot of capability to play with all those tools inside there. One area is important on VFDs is, we have to worry about temperature spacing, what the temperature of the unit's running, because we also have the capacitors and things that are inside, that we have to maintain and keep them, within tolerance. But these are some of the basic programming mode functions that are inside there. And you're able to, just find the data set, scroll up or down with the buttons, and, look for the settings. And then again, what we're back to is these basic functions of your output frequency, the output current, the voltage percentages, the output power rating, that the motor is seeing. And these are display functions in most drives. Your status, source. And then inside they have a, set of control terminals that are, again, like a PLC where, you have contacts here. Your 30s are your, just an extra output relay. So is the Y. Then you have your various, X inputs. So as you go common to X1, it's like gives a run command. You can set X1 to be a run, a stop, or, it gets multiple parameter issues. They come out as standard. And if you look at a drive, most of them have what they call quick start. So you can quickly start the item. Let's see, this shows just a few of the various, assignment pieces of those contacts, like here, the Ys, the relays of what you can do with them. You got your acceleration, your deceleration motor, whether you want it, to coast to stop, ramp to stop. Let's keep going here. So back to what I was talking about were the those ripples on your input. If you look at it with a scope, you will see these extra voltage ripples that happen, and they're called harmonics. On a three-phase circuit, you get a fairly high fifth, a third, and a seventh. And then you get a resultant of, this is the amplitudes of that value. That's important because that's what the input then starts seeing to the rest of your original power source. So you need to be aware that these always try to go find their least resistance to ground of where to get it done. So it's very important that you do proper grounding on VFDs also to get rid of those voltages. So this is a look at those spectrum frequencies that show up, and these are the percentages of the current of the RMS percentage. So if you're drawing 100 amps, you'll have like here up at 23 amps of that are fifth harmonic currents, and you don't pick those up on regular meters. And so it's important that you are aware of that. We'll get back to that. That's about looking at a voltage spectrum. So what I want to get into is causes of failure. My father was a past chapter president of ESA. This is an electrical mechanic authority group that is scattered across the world. There's over probably 5,000 members of this group, companies, plus many manufacturers, that also share their insights and ideas to build high quality project applications and high quality reliability in motors. And so they have this little book, I call it the ESA Bible. But inside this book comes with must have like 150 pages. There's a little copy of it. And of all of those pages inside, I did pull out today an area of issue that needs to be concerned with, is that it is back to this picture of voltage balance. So the input voltage of a motor doesn't always stay consistent. It goes high, it goes low, unbalanced. And from that in here, it gives you the duration factor. So an area that gets overlooked, especially in irrigation, where we're out in a rural, location, you don't get good voltage balance. And so if it is off in the chart, it shows that it's off by, 5%. So that is pretty common, but the actual duration factor on the winding of its length of reliability to maintain its original design point, you should derate that motor by 25%. And that doesn't seem to be happening a lot. A lot of times everybody's running it, into the service factor. And so the motors tend to run hot. That's on the voltage imbalance. It also, over here, this chart shows that a motor winding was originally designed to be its best magnetic point, was what the nameplate said. So if it's 460 volts, as it goes higher or lower, again, then what happens is the heating factor inside the motor becomes warmer and warmer. Plus, then with the implementation of this output PWM on voltage here, you don't get perfect clean sine waves. So you end up creating additional, loss factors. So that's why it's important, as you do choose your various controllers and information that you're using, is that you find out how clean are they building waveforms. There are various designs, types. A lot of things get put in by, cost factor instead of, longevity factor, and, the initial cost of something compared to the having to take it apart, or the downtime or losses in production, are much higher than, maybe spending an extra few bucks at the start of the, the application. So I do recommend that you, ask these questions of the people that you're, working forward with. The other area is that happens a lot in submersible application is cabling. And I briefly discussed a little bit about the output cabling lengths. It's important that we also look at the noise factor that comes about because of that PWM. So that's why a lot of discussions that are going on today are about having isolated, shielded cables that come out of VFDs, especially if you have major lengths, meaning that it basically has a shield that goes around the outer plastic that goes also in the cable, so that the motor leads, or the output leads, don't start cross-talking. I've seen it, happen, quite a few different times. You'll see the cable plastic shield will actually, on the outer shield, if it's been on PWM for a while, will actually, start peeling off that outer plastic. And the cables will run hotter. So it's important that you also look at the longevity of life of it. And so when you put that outer shield on it, you ground that off, you get rid of that extra noise, and it actually, does you a lot of favors. And then it's also the sealing of those connections, because they're down in the water. There's a lot of, various boots that you crimp together, and then you pour in the resins or various types of connections before you, drop them in. But make sure those cables are done up very well. Also, the connections going inside, how the motor design was designed, how it seals it, going into the motor, and then back to the corrosion factors of, especially like in desalination, where you're a lot of salt water, to make sure that those are, very capable of that type of an application, because, you set it in there for a while, and then after, a few months, it immediately starts corroding, starts pulling itself apart. Well, it's too far when it's, down the hole, or, out in a, application. I did want to bring up, this device has been a very helpful tool to me. I don't represent Fluke, but there's other manufacturers out there that, are capable available, but I do have one of these. And it's been very helpful to me. And the reason is it basically shows me what is and is going on, and I'll let them discuss what we're looking at here.
Introducing the Fluke 438 Power Quality and Motor Analyzer. The Fluke 438 is a multi-purpose test tool designed to improve troubleshooting on electric motors and minimize downtime. Whether you're in a process plant or discrete manufacturing, electric motors are critical to your operation's success. The Fluke 438 lets you quickly gauge electrical performance, power quality, and mechanical performance of industrial motors. Using three-phase electrical measurements on the input and motor rating plate data, the 438 calculates torque, the most critical mechanical performance variable, speed, load on the motor shaft, and overall efficiency, without the need to install mechanical sensors. All this with a single tool, and all while the motor is running so you don't sacrifice uptime. Power quality issues, such as unbalance in harmonics, can cause motors to run hot, eventually stressing windings and accelerating failures. Motor failures lead to costly downtime, and the cost of waste associated with inefficient motors adds up. When testing direct online motors with the new Fluke 438, you get both power quality information and mechanical performance data in the same test with a single tool. With an intuitive user interface, optimized current probes, and at-a-glance motor status screens, the Fluke 438 gives you the motor troubleshooting information you need to make better maintenance decisions and keep your plant up and running. Contact your local Fluke representative to learn more.
So what we're talking about is it gives us the scoping capability to look at that voltage waveform, the actual current waveforms, and you'll actually see these pulse ripples going into a VFD. And from that, you can then get the overall view, and you're able to even see the effect of this harmonics that happen inside. You'll see the effects on the waveforms, which are very key, because the cleaner we keep it back to the original waveform that Nikola Tesla had in mind, and the cleaner we keep that to the motor itself, the happier it becomes. So from that, once you start seeing these values, it's also important to understand the effect. So there are various devices out there which are different types of what they call harmonic filters, both for the front end side and the back end side of those drive components, which are basically built up with, these are coils inside here, which is basically an inductor, and they put it on all three phases. And those coils resist change in power. So as you put power to them, an inductor doesn't want to immediately take it. It has a delay. Well, then they also put capacitors on here that are tuned in microfarad size, that are connected across in parallel across the circuits. And what that does is it actually absorbs some of those higher frequencies information, and those have to be more what they call a tuned filter. The resultant is that it actually cleans it up. So this showed the original waveform. You could see how it was affecting the voltage itself. Then it showed as this PWM was carrying through in the current, it was putting out 451 volts at 138 amps, where when they put the harmonic benefit filtering on it, it actually cleaned it up. So it also brought the resultant voltage to 443 volts and 128 amps. The power reduction on that on the same load ended up being almost 10 kilowatts difference from using it this way. And that 10 kilowatts is what's going into your motors or leads and cables and actually lost power. So it is an important factor, and that 10 kilowatts, if you take 10 kilowatts and you do the math on that, 10 is roughly 80,000 kilowatt hours. 10 cents a kilowatt, that's $8,000 a year different in operating cost, by where is the harmonic capability proper in an application. That second. So it is important to look at these factors as you're going forward, to maintain that cause and effect issue that happen inside the motor. I apologize for these yellow lines. They keep showing up, but I'm not hitting that button, but must have a little difficulty on my screen today. Again, the cable issues. The other is loss of cooling on a motor. So a submersible motor running in cold water application really doesn't have quite that much effect, but it is a factor when you're looking at a horizontal or vertical motor, that if you lose that cooling from dirt, dust, debris, it again goes back and affects those coils that are inside the motor that end up get an opportunity for failure. We'll go back to these curves here, but ESA also gives us a motor tells a story, because you can see the various phases, back inside the motors. You can see this motor here. This is where the winding charred. It's a very key indication to see on that is you can see that there was a phase loss, meaning that there was no power going through this phase. So these other phases, these other two phases in here carried the load, and the motor would still have the torque requirement on it. And so the motor would start to slow, and then these would, heat up over a period of time and burn out, left these unburnt. And so you can tell that had a phase loss. One of the lines were lost. This shows here an internal, voltage spike, so that as the leads and the power come into the winding, you can see that this ended up having a surge. So that probably had a high voltage coming off of either if it's direct connected from the power company, or had a high voltage surge, from the VFD, could have been from long cable lengths. And it ended up, shorting here, and then the motor has to be rewound. This here typically happens, you'll see a slot failure, typically happens when the motor rotor actually has a bearing failure, and then you start getting scrubbing of the rotor against the stator. And then it heats this up and it loses its insulating characteristics to ground. And so it shorts in the slot and shorts to ground. This one is actually showing that the actual insulation here in the motor actually shorted directly to ground. So again, that could have been a high voltage potential between line and ground that was higher than normal if it doesn't have debris in there, the cause of the deteriorated insulation. It also can happen because the insulation itself, the motor may have been running hotter, and so what happens is that it starts breaking down that paper. It's a paper. A lot of times, like in Class H insulation, which is very high temperature, that's called Nomex. They also, original motors were designed with they have like different characteristics, like an A, most are a B, C, and D design. But the insulations were B, F, and H, meaning that the B was rated to really not run much over 120, 130 degrees, or it had failures. So a lot of the original motors had a lot of copper and iron in them, and a lot of magnetic characteristics. They didn't saturate it very far. So the life of the motor and the cooling of the motor was very critical in the old, U-frames. Saw a lot of airflow going through them. And it was important so that you didn't overheat this. Then came out Class F insulation, which was 150 degrees C, operating max temperature. And then they came out with H now, which is 180 degree temperature. So what actually I like to choose is motors that were actually built with a B temperature rise, and go with Class H insulation. So the benefit to that is it gives you a lot of capability over time to make that motor last. That's why, I've seen motors that are, 50 years old and still operating, and, without failures. And a lot of it has to do with, is heat and temperature and application. So this information is available, and you're able to go to EASA. They're out of St. Louis. You can join if you'd like, and be a part of this grouping, and then you can actually get access to a lot of the capabilities. It also gives you access to people around the world that have extreme knowledge in motor. Various people are certified. They have a group of engineers that are high capabilities from all over the world. I've got many friends in the industry, from Australia to England to Germany, all over the world that all join together. We have an annual conference. This year's is in St. Louis, where we get together and we, talk motor talk. I guess I was born in a motor, so I continue to live there and enjoy it. The other area on pumping application that I want to talk about is it's very important to understand pump curves and where is the optimal sweet spot of those motors and pumps that want to work together, that are optimal horsepower with the optimal, lift or head feet that we're going against. And then, where is this is the brake horsepower, this is the total feet of head. And then this is the, where is the impeller turned and cut to for that given speed that give its best performance. So we get the highest percentage of efficiency of the pump curve running on the motor, and the motor is running within tolerance. So the issues is the design point of the pump itself originally, and the design point of the motor itself. So I highly recommend, these efficiencies can fall way off the curve, by then extra effect that happens, as it falls in and out of its optimal point here. So you'll get such things as water hammer. You'll get, a lot of, effect of surging, motors, especially if you're, at the higher point of, where are you on the head pressure, dependent on, where was that pump impeller cut and turned to at that given speed to give you its optimal performance. Is everything likes to be balanced. Our whole world likes to, operate. You have a balance in operation, and keep it in, its best spot, better. And then this is satisfactory. But you can see cavitation, run out, reduce bearing life, seals, all that. It affects the reliability of that motor and definitely the reliability of the pump. This piece of software is available for a guy that I know down in Australia that actually designed a software that you can actually load in. Where are you going to be running the speed points of the VFD? And then it automatically then calculates where is that optimal percentage, because these curves all change based on speed and impeller size and RPM. So if you go adjust the speed and you haven't pre-checked, you may, by the time you slow it down here over a small amount, I see a lot of people slow a VFD down, even to like 55 Hertz, instead of running at 1800 RPM, it's running at 1700 RPM. If it's too close on that pump curve of where its design point were, all of a sudden it goes right into cavitation and the motor starts having trouble or just totally stop pumping water. So that's where you need to take into effect the actual upper and lower limits, that you set those properly in the drive control so that they're set not to be, out of this pump curve range. And this is the only tool I've seen in the marketplace that you can actually, plug that in. His name is Rob Wilkie. If you want to send me an in-mail or an email, I'd be glad to, connect you with him, and you can access, he has a class that he, teaches around the world, in pumping. He's got about 40 years experience. He's in his 70s, very highly qualified. He's done more pumping applications, than I've seen, most people in the world. And he really stresses back is, where is the optimal pump efficiency point? And then back to irrigation is, are we pumping at the the optimal efficiency point, and what is the total acre feet of water that we're producing for the application. Is that the amount that we need? Because as you slow a pump down, yes, the horsepower drops by the affinity law, but the horsepower drops, but the GPM also drops. So you've got to look at total acre feet trying to get to a crop application to maintain that. So a lot of times you may just be running longer, and your total kilowatt hours, even though you got a VFD on, that you were expecting a 30% cube loss savings, ended up being negligible, because you also have losses in the drive control itself, of the drive itself, these transistors and components inside here. You get losses in your transistors, you get losses in your capacitors. It ends up being about an average about 3%, power loss, through the device. Normally it's negligible when you're saving 30%, but it's not when you're looking at total acre feet. So I do highly recommend that you look deeply, at accessing this software, prior to installing or purchasing a VFD. Definitely in irrigation. He's shown many times how you can, save 20% by just getting the pumps, trimmed properly, getting the speeds operating to the correct points, and then just using a soft starter, which has zero losses, on the input, and just start the motor slowly, because you also, one other point I want to bring up in that on starting is, a VFD has normally 2 or 3 set points that you can start the motor, so you can accelerate it up to a point of pumping. When it's going to start building the potential water hammer, you can accelerate it quickly up to load that thrust bearing. And then as it gets to that point, then you can bring it on up into speed. So you bring the first acceleration up to, let's say, 30 hertz, where it starts pumping water quickly, normally within like 2, 3, 4 seconds. And then you can set the acceleration on the second stage acceleration, set that out to a longer period of time when the thrust bearing's loaded properly, and you're going on up in speed, so you don't want to create water hammer in the hydraulic circuit. So you're able to slowly bring that up to the next stage, and do that, maybe 30 seconds acceleration on the second to eliminate that water hammer. Most of the time I see a lot of guys on the slowdown of a motor or stopping is they go to coast to stop on pumping applications, because that water running back down the column has power, and so the motor, because it's still in there rotating, creates and becomes a generator and starts creating counter EMF back. So that's, if you leave that connected to the circuit, you'll end up getting over voltages when you shut it down if you try to decelerate it too fast, because the circuit is actually acting as a generator and feeds it into the capacitors. Over voltages the capacitors said, no, we don't want to blow a capacitor out. So then it trips on over voltage and lets it go coast to stop. So I like to set most pumps to coast to stop, unless you're really needing to control the circuit on a pumping application. This also is a tool, if you want, you can aggregate over time, when the pump is running, when it isn't running, to actually, do a calculation of, what you can save in power on the VFD over time. And is it a pumping, a fan, inlet vein, outlet veins, again, throttling, not throttling valves, to determine what your true savings will come out, in a given application. The tools, that are out there, you got your standard voltage metering. This doesn't measure any of the harmonics or detail. You got to go to what they call true RMS metering to actually see all the spiking. And I found this one to be easiest to use in the market that I've found. These are price range of 150 to 300 US dollars for a standard, just a voltage meter that also can have, current clamps on it if you want to measure the current. These run anywhere from 5,000 to 7,000. Actually, they're kind of older numbers. They have increased in price some, but it does give you that scoping look at all the details, and by understanding what that tool can do, can save you thousands and thousands of dollars in operating cost and reliability. These are what they call hobo meters that you put in to look at things over time. So you can actually, they have current transfers that come with them, and they connect in. What they actually do is they just record it over time so that you can actually look at what is the real operating cycle and load cycles, of those pumps and applications. You just stick those in the cabinet. They're fairly small, leave them in there and take a look at it. That's the failure. It's a trifold form. The book also has, the calculations of, calculating pump horsepower, to GPM, your pressure, your volumes. Very useful tool. I've went for about an hour, and as you can see, I could talk for hours. I love what I do. I love this industry. Always have been fascinated by it. Been very blessed from it. It's given me a lot of, opportunities and things around the world, and I have been fortunate enough to be able to travel the world from it. This is my contact information. Again, my name is Roger Fritz. Send an engineering AC-DC hotline, any questions you have. This is my US, number. I'm also on WhatsApp and Signal and a few of the other ones, but please feel free to find that. Again, there's the I'm also very heavily involved in turbine pump motors. Was very fortunate to have this man as a friend, who actually was one of the original designers for US Electric Motors. Sadly, we lost him last year, but he built some of the original designs for vertical turbine motors. Was there when back with US Electric when they originally built the old heavy frame motors. So one company that I do work with is BMR, and we build turbine motors back to the original types and designs, where you have the split cores, grounding rings inside to eliminate any, if you do have harmonics noise, we put spike resistant wire in the motors, again, to make them last. Key important factor. And